a complete picture of our world, one has to put together a lot of elements, a lot of different shapes into one piece of content. We learn from our early childhood to notice when something is missing from a picture. It often happens that we are lacking just a few elements, and if we had them, we would have a complete, perfect picture of our world. Nuclear power plants are terrifying to many of us. Most often the fear is associated with the events that happened a quarter of a century ago, or because of a lack of information. People don't really know how the atom affects the human body, so our public perception is like a puzzle missing pieces. And many of the pieces and understanding whether the peaceful atom is safe or unsafe have to be found. Now, let's try to find out just what exactly is going on behind these thick walls. What is the thickness of the steel doors and concrete walls around a nuclear reactor? External fuel. Why does Russia need fast neutrons? And lastly, what is radiation safety? How dangerous is a nuclear power plant for the environment and each of us? So to see the whole big picture and answer these questions, we need to take a look inside the reactor. Only special clothing is required to enter the core of the plant, the reactor. To enter the controlled access area, one simply has to change their clothing. I've been given a hard hat, a special jacket, a shirt, and even these special socks. First, we're changing our footwear, then our hair has to be kept under control, and we have to button up all of the buttons on our uniform here and get a dosimeter. Hello. Hello. Thank you. Everybody who enters here gets one. Today we have to find out the answer to one more question. Is it dangerous for the staff of the plant to work here because of the radiation? A state-of-the-art nuclear power plant is a very complex organism controlled by electronics. All information flows to the central control panel. For example, the third unit of the Kalinin nuclear power plant is generating 1,000 megawatts of electricity per hour. On the whole, the plant meets one-third of the electricity needs of the Tver region. Some of it is also transmitted to the Nizhny Novgorod and Vologda regions. Russian nuclear power plants now generate about 40% of the electricity in the European part of the country. Both the plant staff and automated systems monitor the peaceful atom operating round the clock. The electronic brain of the plant includes thousands of high-speed processors which trace all the process parameters of the plant. They have a tactical task to prevent running beyond limits, to ensure safety, to deal with processes humans cannot trace in theory. It's a fast response, it's high precision of control, precision of measurement, etc. All of this can be found in our automation. To enter the reactor hall, one has to open these lead multi-ton doors. The distance from one door of the airlock to the other is more than 2 meters. And here is some high-strength, cast-in-place concrete. The container is 6 times thicker than the walls of common cast-in-place buildings. The reinforcement bars are placed there 3 times more densely than in regular housing. Therefore, a leak-tight dome of 45 meters in diameter is capable of withstanding fantastic loads of stress. It will be able to survive a magnitude 8 earthquake, a tornado, a tsunami, or even a jet fighter crashing directly into it. The plant's concrete dome keeps its leak-tight surface at a temperature of 150 degrees Celsius and a pressure of 5 atmospheres in the reactor halls. It consists of 2 parts, an inner and an outer. The inner part is formed by a 1.2 meter thick wall and reinforced by an 8 millimeter thick solid steel sheet. It provides a seal in case of a hypothetical accident. The thickness of the outer shell is slightly less, 80 centimeters, of high-strength concrete, but is reinforced by a special tendon system made tense inside the shell itself. In essence, it is a bracing steel cocoon, which increases compression strength of the concrete by up to 3 times. Only a few people can get inside the reactor hall. They are special employees of the plant. But today we have a rare, unique opportunity. The 3rd reactor of the Kalinin plant has been shut down for scheduled maintenance and refueling. Therefore, today we can come pretty close to the reactor vault. Water with a lean solution of boric acid is circulating inside the reactor. The reactor is started up when rods absorbing neutrons are withdrawn from its core. A large amount of thermal energy is released during the chain reaction, circulating through the core and dousing fuel rods with water that is heated up to 320 degrees Celsius. Passing inside heat exchange tubes of the steam generator, the primary water releases heat to the secondary water without contacting it, thus excluding the release of radioactive substances beyond the reactor hall boundaries. The rest of the process is like at a conventional thermal power plant. Secondary water turns into steam, steam rotates the turbine at a murderous speed, and the turbine is turning and churning an electric generator. And this generator is the device that generates the electricity. As far as I know, nobody's ever filmed anything like this. We have a unique opportunity to touch the heart of the nuclear power plant. We are inside the reactor. This is the water-to-water reactor of the Kalinin power unit under construction. This is the place from which the primary pipes will run. And right here, there will be uranium fuel. Both our and foreign experts believe that modern nuclear power plants are one of the most clean methods of energy production. Since at thermal plants, the burning of natural gas, fuel oil, or coal releases an enormous amount of soot, smoke, and radionuclides, which are contained in the coal, into the atmosphere. Certainly, naturally, nuclear power is much cleaner in terms of environmental safety. You know, it is a worldwide cause for concern, this carbon dioxide, CO2. And in this sense, naturally, we don't like to release so much carbon dioxide into the atmosphere. Exiting the plant, just like entering it, is quite a ritual. First, you have to submit your dosimeter. So over several hours of work right in the heart of the nuclear power plant, we received an exposure dose of 6 microsieverts, while the guideline is 100 microsieverts. Thank you. In fact, we have received a dose that is 100 times less than we receive over a 1-hour flight on an airplane. Then there is one more safety line of defense. At the exit, there is an automated scanning of our clothing. At a nuclear power plant, they are very keen on cleanliness. If radioactive particles have gotten on my clothing or on my footwear, this device won't let me out. Everything is clean. A nuclear power plant is a very complex organism. You can be certain of that when you look at the Novovoronezh reactors, which are currently under construction. Soon the reactor container will be in place here, and the reactor itself will be put in. The turbine hall and Russia's highest cooling tower are nearby. Somewhat later, a similar power unit will appear on this site. An Armenian nuclear power plant suffered severe tests for seismic stability in 1988. On December 7th, near Spitak, a magnitude 7 earthquake took place. Nearly all the northern part of the country was ruined, and only the Metsamor nuclear power plant operated without any interruption.
The plant was built with seismic design in mind. Quite standard engineering solutions were used. Hydraulic shock absorbers, for instance. They are used on each car. The car's passengers go over some potholes, but the passengers don't really feel the bumps or changes in acceleration. All the plant's pipelines were specifically not tightly anchored to special equipment components. This keeps things nice and smooth, loose, and flexible.
Nuclear power plant safety is ensured at the stage of plant design. The design is done using computers and 3D modeling. In the near future, it is planned that supercomputers designed by Rosatoms companies will take over. They will allow for 1 trillion operations per second, and this means modeling of all possible and sometimes impossible abnormal situations will be able to be done quite easily. Today we are carrying out calculations of various abnormal situations and developments. And so far, as per Russian rules and regulations, everything is in order in terms of safety and environmental impact. Computer capabilities, when used for design of nuclear power plants, make it possible to shift to the so-called 6D modeling. In addition to a multi-D design of the plant itself, the computer independently plans supplies of construction materials to the site, calculates their delivery dates, determines a number of construction workers and their skill levels. All of these shorten the construction time for more than a year. As a result, it is possible to trace all process nuances in real time, volume, and color.
We in the whole world and in Russia generally worldwide see how the so-called nuclear renaissance carries on. In other words, an interest in nuclear power and construction of new plants resumes. In fact, the government of each country is to decide what fraction should be nuclear and conventional energies. From our viewpoint, we have to do all the necessary work to make it safe. The reliability of plants designed in Russia has been acknowledged by the world community. Therefore, today, Rosatom holds the world's top position in parallel construction of nuclear power plants. 5 reactors are operating overseas in India, Bulgaria, and, of course, in Iran. No entrance without hijabs. This is Bashir, the first nuclear power plant in Iran and in the whole Middle East, and certainly the first one built by Rosatom, where this Islamic women's garment is mandatory. It's difficult to get used to wearing this blanket in 45 degrees Celsius heat and 100% humidity, but when in Rome. In August, the first criticality program started in Bashir. Nuclear fuel was brought to the reactor hall, and the IAEA specialists applied seals on it. We are very grateful to the people of Russia for all the assistance we were provided, for the assistance in construction and getting hold of advanced technologies. This is a great day, an important historical event. One more element in understanding how peaceful the atom has become in recent years is to look at the building of plant safety systems. Now it comprises more than 40% of the total plant cost. Let's start with the water-to-water reactor. It has 4 safety barriers. The first is the strength of the uranium fuel pellets. They feature double safety margins in terms of temperature. The second safety barrier is the fully leak-tight cladding of the fuel rods. It is made of zirconium alloy and possesses higher corrosion resistance and is capable of retaining shape even at 1,200 degrees Celsius. The third barrier is the strong reactor pressure vessel, which was designed for an operating pressure of 160 atmospheres. And the fourth barrier, which is a leak-tight container around the reactor hull. This multi-layer protection excludes radioactive releases even under severe accidents. You'd have to try hard to bring this reactor down, because if there ever was a deviation in systems operations, the reactor unit control and protection systems can operate both manually and automatically without human interference. In any case, there's only 4 seconds before the safety algorithms actuate. If the reactor unit loses its power supply, for any reason, neutron-absorbing rods drop their weight into the core and the chain reaction starts dying. Then the nuclear fuel, which is heated up to an operating temperature of 500 degrees Celsius. Thus, water with higher boric acid content from a backup tank starts flowing down, doing both cooling of the core and absorbing neutrons. Its circulation is supported by automation, which can keep the reactor in such a stable state up to 1 day and a half. The actual amount of radiation that escapes the facility is equal to about 10 million years of what you would gather normally. This value is so small, just to give an example, that it would be like, say, the probability of a meteorite hitting the head of a person who is crossing a field. The safety level is so high in today's reactors. In spite of complete automation, the personnel of the nuclear power plant do continuous training the mast or fighting the chain reaction manually. This training is at computer-aided facilities like these training centers. In the event of any deviations from normal operating procedures, automated systems are clicked on. But certainly, an operator is in control of its performance. Even if all protective barriers have failed to retain radiation, there is one last safety system. Specialists call it the core melt trap. This last line of defense intervenes when it is not possible to cool down the reactor and fuel temperatures have run up to 2,500 degrees Celsius. In this case, all internal structures of the reactor melt down, and the core melts and flows with reactor pressure to the vessel bottom while destroying it. This radioactive magma immediately gets into a special cooled concrete bucket. It is filled with so-called sacrificial materials that can reduce the melted material's temperature to 1,700 degrees Celsius. The core melt trap design provides for water cooling that prevents the melt from destroying the reactor hull containment. For the first time, the core melt trap was used at the Tianwan nuclear power plant in China. This is a domestically made design. The plant was started up in 2007 and released for commercial operation in 2008. That's where our national development was used. Now it is included in all up-to-date projects of plants under construction, in particular in the AES 2006 project, which is underway at the Leningrad site, the Novovoronezh site. The core melt trap is employed everywhere. But not everybody in the world is rushing to use this design because these are currently costly measures, which cost money. But Russia doesn't economize on safety. Finland actively cooperates with the state and other bodies of Russia in nuclear power. And there is an opinion now that nuclear power in Russia is quite safe. Given what I know about Rosatom's nuclear and radiation safety program, I believe it's very effective. And one more element of safety, management of spent nuclear fuel. Once in 4 years, each nuclear reactor is specially shut down to replace nuclear batteries. Fresh fuel is carefully put into the reactor using a special manipulator, and the spent, still radioactive, used fuel is placed in a so-called hold-up pool. Here, in distilled water, the fuel pellets are gradually cooled. After 3 years, they become less radioactive and acceptable for shipment and reprocessing to the Mayak facility in the Chelyabinsk region. This is the storage pool of Russia's only facility for reprocessing spent nuclear fuel. Right now, under my feet, there are 3-meter-long fuel rods from a nuclear reactor. Specialists say it is absolutely safe to be here because the water is a reliable shield. Cooled down fuel rods are sent for fractionation and dissolution. Uranium and plutonium are recovered using the chemical extraction technique. They will be used to make fresh fuel for nuclear power plants. Uranium and plutonium decay products are also recovered from the spent fuel and then used at the Mayak facility to make ionizing radiation sources for medicine, industry, and science. The waste remaining after processing just 3% of the uranium from a former fuel rod is sent to the high-temperature furnace for vitrification. In this furnace, a real glass is made of the waste, poured into cans and contained, and after cooling is sent to the underground storage facility. The waste becomes part of glass. This is the most efficient way of waste disposal. It is used all over the world. Such countries as Germany, the USA, the UK, and Japan long ago came to the conclusion of using this technique and acknowledge it as the most efficient way, since glass is very stable to corrosion, i.e. it is corrosion resistant. It has a very low leaching factor, i.e. it is difficult to wash different components we put in there from it. Specialists across the world believe that spent fuel of up-to-date nuclear power plants is not radioactive waste, but a valuable feedstock for new generation reactors, for fast neutron reactors. Here is the hope of the domestic nuclear power industry, the BN600 reactor. Today, Russia is the only country in the world which possesses the technology to design and operate these fast reactors. This is the near future of nuclear power and is the answer to the question of what to do with already spent nuclear fuel. The fuel for fast reactors is spent fuel of water-to-water reactor. Plutonium required for starting up a reactor is extracted from this fuel. Certainly, spent nuclear fuel inventions in storage facilities can ensure at minimum 200 years of continuous chain reaction in fast neutron reactors. In addition, they are capable of digesting uranium-238, which is not used by modern nuclear power so far. Thermal nuclear reactors which operate worldwide use uranium-235, which is just 0.7 of what's in nature. It means the difference between a fast neutron and thermal neutron reactor is that the former can use uranium-238, i.e. uranium, which is not used in nuclear power, and it can be involved in the nuclear fuel cycle. Uranium-plutonium pellets are used as startup fuel in the fast reactor. This increases neutron flux density by 1,000 times as compared to the water-to-water reactor. The coolant here is not water, but liquid sodium. It is transparent for neutrons, which are bombing fuel pellets at a high speed, while heating them up to a temperature of 700 degrees Celsius. In the core, besides uranium-plutonium fuel, there are assemblies with residual uranium-238, which turns into nuclear fuel for conventional nuclear power plants under the impacts of fast neutrons. Capabilities of fast reactors look nearly fantastic to our eyes. During the nuclear reaction, they do not burn fuel, but breed new. When all BN fuel is changed, once in 3 years, 100 grams of uranium-238 yields 120 to 140 grams of fresh nuclear fuel for conventional nuclear power plants. Therefore, very often, fast neutron reactors are called breeders. At our university, I remember the first lecture, and our teacher was asking us, what is a fast reactor? He gave us one example, a stove. But in a normal stove, we don't gain energy. This is like a stove where you throw in 3 logs to burn, and you pull out 4. This is the concept of the fast reactor, so to say, i.e. production of fuel, which can then be used in the next reactors. In essence, it means waste-free generation of atomic energy without damage to the environment. The nuclear specialist will just have to choose the right proportion. Each 4th reactor in the country should be of the fast neutron type. In conditions where the natural uranium resources are depleting worldwide, Russia is getting ready for a nearly unlimited energy resource supply for several centuries. Looking into the near future, Russian scientists are not satisfied. They're working to create smaller, even faster neutron reactors.
Different power capacity gives us different management techniques, different construction methods of these facilities. It means that we can begin with a small power, so-called jewelry button battery, which can be used for small rural communities, and proceed to larger capacities which can cater a whole town or large industries.
Могут обеспечить потребности больших производственных промышленных предприятий.
Nuclear reaction in this type of reactor doesn't require high pressure, and the probability of radioactive releases is nearly absent. The compact size of the peaceful atom will allow it to be brought to any place in the world, just like an email to a computer. It could be sent to a remote village or to any sort of work site. This will be a real revolution in power generation.